All right, today what I'm going to show you guys how to do is how to predict the amount of products you get from chemical reactions. That's what stoichiometry is. But it's really some simple steps. And there's one thing I always tell people is the middle step you do in these equations is really the only thing new that you haven't done before. And you also have to understand that when you want to predict how much products you get in a chemical reaction, the key to that is having a balanced equation. That determines how much product you actually get. So for instance, we have this equation here, between nitrogen and hydrogen that produces NH3, is called ammonia. The first thing you have to do is balance it. And what that equation then tells us is once we have it balanced, it means that 1 mole of N2 will react with 3 moles of H2, and then we'll get 2 moles of NH3, and that can never change. And so that actually allows us to predict how much product we get. Because for instance, let's say we just happen to have 2 moles of N2 and we want to know how much ammonia we'll get. Well, it's a 1-to-2 ratio. So if 1 mole of N2 is going to get us 2 moles of ammonia, and that never changes, 2 moles is obviously going to get us 4 moles. It's still a 1-to-2 ratio. Just like 1 mole, if it reacts with 3 moles of hydrogen, that means then that 2 moles would react with 6 moles of hydrogen. It would still be a 1-to-3 ratio. So the key to all of stoichiometry is just having a balanced equation, which you've done before. And then the first step you do, so up here you see a series of steps that you do for all stoichiometry problems. This is actually step 1 here. So this is step number 1. And basically, if you don't start with moles, this is a mole relationship. In other words, 1 mole of this reacts with 3 moles of that and 2 moles of that. So since the balanced equation is a relationship in moles, if you start a problem with particles, a mass in grams, or volume in liters, the first thing you do is convert it to moles. And you've done that already because there's our mole map that allows us to do that. And so, if we started with particles and we wanted moles, we would divide by 6.02 times 10 to the 23rd. If we started with grams of something and we wanted to know how many moles it is, we would divide by the molar mass. And then if we started with a volume in liters of something of a gas and we want to convert it to moles, we divide by 22.4. So the first step and actually the third step is simply the mole map. I mean, it's just the mole map turned on its side is all it is. So this is step 3 in stoichiometry problems. And all it's saying is, well, you go from moles of, in this case, reactant to moles of product. But if they want an answer in something other than moles, like particles, mass, or volume, then you would you would multiply by 6.02 times 10 to the 23rd, multiply by the molar mass, or multiply by 22.4. And the conversion factors are given here. They always list them right next to it. And so I'm just going to show you how to go about this in a simple way by condensing everything so you're not just having to do just one step at a time. You can put it all together and then calculate from there. The only thing, so this is obviously then, if that was step 1 and that's step 3 with the mole map, this is step number 2 here, and it is the only thing new that you're doing in stoichiometry, but this is the middle step in every single problem, and it is the one thing that must be done. Like, you have to do the middle step before you can go from step 1 to step 3. So let me show you what I'm talking about here with these problems. First thing we've got to have is a balanced equation. And again, from there, we need to, let's read what they're asking for. So they say we've got 0.6 moles of nitrogen. We're going to go to moles of ammonia. That tells us where we're starting. Now, you only do step 1 if you're starting with something other than moles. We're already starting with moles in this case, so we're already right here. So you'll see most of these equations, we're going to start with something else. We'll have to do that first. But so for this problem here, we're already at moles of what's given. So we already have 0.06 moles of N2. That's what nitrogen is. So this is moles of what's given. And what you'll do, so we're right here, we're going to go to moles of what we want. That's always the middle step. You got to go to moles of what's given to moles of what you actually want with this step. Notice it says moles of the new substance over moles of the given. That's going to be our conversion factor here. So what do we want? They're asking for ammonia, so we're going to go to moles of NH3. Again, I know that's something you're not familiar with, but that's what ammonia is. It's NH3. And so remember, when we've been converting all year, when I say what goes at the bottom of this conversion factor here, it's always the preceding unit. Not the numbers, but just the preceding unit. So we started with moles of N2. So moles of N2 will go there. And again, like I say, this is the only new step. So where do I get these numbers? You get those numbers every time in that middle step from the balanced equation. So what number's in front of NH3 on that balanced equation? 2. What number's in front of N2? There is no number, so it's understood that there's 1. So now you just multiply, cross, and divide. You are done, because this question is only asking for moles of the new substance that they want, and or the wanted substance, and you stop right there. So it's just a one-step problem. We went from moles of what this is always moles of what's given, and this is always moles of what we want, and that's all that equation was asking for. So we do that. 0.6 times 2 is 1.2 moles of NH3, and that would be our answer. Now, again, if you go back and look why this equation says for every 1 mole of N2, you would get 2 moles of NH3, if that's how much we have. The problem said we only had 0.60 moles of N2, so how much NH3? Well, we would get 1.2 moles of NH3, because 0.6 to 1.2 is a 1 to 2 ratio, and that's why this always will tell us, the balanced equation will tell you how much you're going to get in the problem. All right, moving on. Let's see, I'm going to skip this one. Again, if you want to do them on your own and ask me later what the answer would be, I would certainly do that for you, but I'm going to try to save some time here. So the next one here says, calculate the number of grams of NH3 produced by the reaction of 5.4 grams of oxygen. So we got, we got 5.4 grams of hydrogen. Don't worry about the fact that it says excess nitrogen. What we want, they want to calculate the number of grams of NH3 produced. So you always have to know where you're starting and where you're going in these problems. This is still based on that balanced equation up here. Again, it is N2 plus 3H2 produces 2NH3. All right, so here's what to do now. First of all, write down what you have. You got 5.40 grams. Don't forget, hydrogen is a Brinkhoff element. It is H2. Now remember, in this case, we are not starting with moles. We are starting with grams. So we actually have to do step 1. We've got to convert that to moles. That's all you're doing. So if you're starting with something other than moles, you're just using a conversion factor to convert it to moles. So we're going to do that. So if you don't start with moles, that's the first thing you do, go to moles. Okay? What unit did we start with? Grams of H2, that's what goes here. And then we would say 1 mole of H2 is how many grams. Again, they're telling you this up here. This is the conversion factor you actually use to get to moles. So they're telling you that. And so 1 mole of H2, again, you get that from the periodic table. You look up the molar mass of hydrogen, it weighs 1, but H2 obviously then would weigh 2. So now this gives us, again, moles of what's given. We are now here in the problem. So we're now at moles of what's given. But this is the only thing new that we're doing now. We got to go with moles of what we want. So what are they asking for? They are asking for NH3. Now I know they're saying grams of NH3, but you can never skip the middle step. You got to go to moles of what you want before you can do that. So you're going to go, because this relationship in this equation is in moles. So we're going to go to moles of NH3. And then again, we always cancel when you go, what goes here? It's the preceding unit. Whatever we started with and the conversion factor before goes there. And then the question is, where do you get these numbers? I always put a box around that. That's the only new step. You get those numbers come from the equation. That's where those numbers come from. So you go up there, there's a 2 there, and there we started with hydrogen and a 3 there, and we canceled those out. So that'll give us moles of what we want. Now we're right there, but in this case, they want to know how many grams of NH3 we get, and we can do that. It's a simple step. You have to understand, once you get moles of whatever it is they're asking for, you can easily convert that to any of these things. You can convert it to particles by multiplying by this number. You can convert it to mass, again, which is what we're going to do by multiplying by the molar mass, or you can convert it to volume if it was a gas and multiply by 22.4. So we just have to see what they're asking for. They want grams of NH3 over moles of NH3. Again, preceding unit goes there. 1 mole of NH3 is how many grams? You find that from the periodic table. Go look them up on the periodic table. Again, see what they weigh. Nitrogen weighs 14, and it's 3 hydrogens attached to it. Each one of those weighs 1 apiece. So the mass of that is 17. And then we got to calculate that, see what we end up with. So 5.4 times 2 times 17 divided by 6 total at the bottom, and we end up with 30.6 grams of NH3 that's produced. And that's stoichiometry. That's essentially all we're doing is converting to how much product they want. You could be going from product to reactant as well, but you would do the problem exactly the same way. So, all right, let's move on to the next problem. Let's see what we got there. And so the first thing we need is the balanced equation from that. And so it says how many molecules of oxygen are produced when a sample is decomposed. So water's decomposed. So again, we got, what is our reactant? It is water. If we're going to decompose it, you're going to end up with H plus O. There's a problem there. They do not exist that way. They're diatomic. They're Brinkerloff elements. So it's H2 and O2. And then it's not balanced now. We got to balance it. We got only 1 oxygen there and 2 over there, so we got to put a 2 there. That gives us 2 hydrogens. So now we have a balanced equation. And again, this is the key to all of it. This is saying that, again, 2 moles of water is going to get us 2 moles of H2 and 1 mole of O2, and that'll never change. So if this amount they've given us here is, let's say it's 15 moles of water, how many moles of H2 we get? We'd get 15. It'd be a 2-to-2 ratio. And if this was 15 moles of water, they want to know how much oxygen, it would be 7.5 moles because it's a 2-to-1 ratio. So again, I'm just going to squeeze all this together into a stoichiometry problem. So you get 29.2 grams of water. They want to know how many molecules of oxygen are produced. So again, we've got to think about where we're starting on these problems. I'll use that previous copy there. So in this case, again, we're starting right here with grams, and the first thing we got to do is convert it to moles. So we've got 29.2 grams of H2O. We need to go to moles of H2O over grams, that's moles by the way, of H2O. And 1 mole of water weighs 18 grams. And then, so that'll give us moles of what's given. That's what you always do. We get rid of our previous unit. And then remember that the middle thing we do, the only new thing we do in these problems in this unit is we go to moles of what we want. And what do we want? They want molecules of oxygen, but you can't go directly. You always got to go to moles of what's given to moles of what you want. And that's oxygen that they're wanting. And again, that's the middle step you do on any stoichiometry problem because this relationship up here is in moles. And then previous unit goes here, moles of H2O. Got to get rid of that. Now the question is, where do you get these numbers? You always get these numbers again when this middle step on the stoichiometry problem, you get them from the balanced equation because that is going to get you moles of what you start with. And if you know how many moles of what you start with, the next step is to multiply by the molar ratio that's given in the equation. What number is in front of O2? There's no number, so it's understood to be 1. And then the number that's in front of H2O is 2. That's where these are coming from. And again, so if that gives us 0.5 moles, and we want to know how much water we're going to get, it'd be 0.5 divided by 2, because it's a 2-to-1 ratio. 0.5 of this would give you 0.25 of that. All right, now you got to go, they want, in this case, they want molecules of oxygen though. So again, we're going to go to molecules of O2. Again, preceding unit goes at the bottom of that conversion factor. This again is just the third step on these problems. So in this case, again, we ended up with moles of what we want. Now a molecule, remember, is a particle, and we're going to multiply by 6.02 times 10 to the 23rd because that's how many molecules are in a mole of anything. So 6.02 times 10 to the 23rd. Now you'd say 29.2 multiply across times 6.02 times 10 to the 23rd divided by 36 to get your answer. And I'm going to show you real quick in the calculator. It's not going to be real fast, but 29.2 times 6.02 second EE23, and then divided by 36. There's our answer. Don't make the mistake that I see a lot of people do and say that the answer is 4.88. The answer is 4.88 times 10 to the 23rd. So you see the E23 at the end. So 4.88 times 10 to the 23rd molecules of O2. All right, moving on to the next problem. So in this case, it says sulfur dioxide reacts with oxygen to form sulfur trioxide. So we've got to make a equation or a reaction out of that. So sulfur dioxide, that's SO2. It's a molecular compound. The di means there's two oxygens. Reacts with oxygen, remember that's a diatomic or a Brinkhoff element, and produces sulfur trioxide. Then we got to balance it, and we're going to have two of those, and two of those obviously. Now we got 4 oxygens there and 2 there, and a total of 6 over there. So now we have a balanced equation, and we can do the problem. So we got 19.8 liters of sulfur trioxide. They want to know how many grams of oxygen we're going to get. And again, we just deal with it one step at a time. You know, what's the first thing you're doing? You are, again, we're not in moles, so we're starting with, we'll write down what we start with, 19.8 liters of SO3. First thing you got to do, convert to moles of SO3. That's what we always do. We figure out where we're at here. And again, we're in liters this time. We're going to go to moles. We got to divide by 22.4. There's our conversion factor right there. They're telling us what to do. So liters of SO3. Remember, we got to cancel the preceding unit. 1 mole, 22.4 liters. That'll get us moles of what? Again, moles of what's given. And then remember, we got to go to moles of what we want because this is a molar relationship in this equation. They're wanting grams of oxygen, but you got to go to moles first. You got to go to moles of O2. Preceding unit always goes, you know, at the bottom of the next conversion factor. Gets rid of that. Again, this is the only new thing we're doing. We get those numbers from the equation. There's a 1 in front of O2. That's where we're getting that. And then there's a 2 in front of SO3. That's where we get the molar ratio from. And then they want to know how many grams of oxygen. So they want grams of O2. Again, over moles of oxygen. 1 mole is how many grams? Oxygen, again, you can look it up on the periodic table. It weighs 16, but there's 2 of them. So it'd be 16 times 2, 32 grams. Then you multiply across. 19.8 times 32 divided by 44.8, you get 14.1 grams of O2 as the answer there. All right, looks like we got 2 more problems to do, and we'll be done with that. So again, we've got 5 grams of potassium chlorate, and they want to know what volume of oxygen gas is produced. So first thing we've got to do is make an equation out of this. So we've got potassium chlorate. Now you're going to have to know by the fact that it's chlorate that that's actually K, and chlorate is ClO3. I am crossing charges to put them together right. They're 1 and 1. And then it says to produce potassium chloride, you're going to need to know that that's KCl by the IDE ending. Their charges are 1 to 1, so I put them together right, plus oxygen gas, and that's diatomic, so you can't leave it as O. Now it's obviously not balanced. I'm going to put a 2 there to balance the oxygens, because we got 2 over there and 3 over there. It's an even odd situation, and then we'll put a 2 there. So now we have a balanced equation for that. And now we can proceed and do the problem. So we get 5 grams of potassium chlorate. They want to know what volume of oxygen gas we're going to get. Hopefully at this point we're just doing these problems exactly the same way every time. That's the one thing I can say about stoichiometry. You know, we have people that get it and that don't, and sometimes we get some of the highest grades of the year with this stuff because it's just, you know, you're doing the same thing over and over again. So you just got to know what you're doing to start with. So you got 5 grams of KClO3. Again, are we starting with moles? Just like we've done every single time. If the answer is no, you're not starting with moles, the first thing you do is convert to moles. So KClO3. Again, what units go here? Whatever you started with, KClO3. 1 mole is how many grams? Where do you find that? From the periodic table. Look up what K weighs. Look up what, again, sorry, can't see it in there. Look up what potassium weighs and what chlorine weighs, and 3 oxygens, and add them all together. It weighs 122.4 grams. And you remember, that's moles of what's given in the problem. Then you always got to go to moles of what you want. We're wanting oxygen gas. So go to moles of O2 over moles of KClO3. Again, this is the only new step. Get those numbers from the balanced equation. There again, the 3 there. What's in front of KClO3? 2 there. And again, after that, they want to know what volume. So they want to know liters of O2 that we get. And again, 1 mole of O2 is how much? Is 22.4 liters. And then multiply across, then divide to get your answer. You get 1.37 liters of O2. And again, notice it didn't matter. You just got to know where you're starting and where you're going, and to get your answer there. And you can use this to do every single problem. You know, if you go, well, what do I do in the beginning? You know, do I divide by 6.02 times 10 to the 23rd? Do I divide by molar mass? Do I divide by 22.4? It just depends on what you start with. You know, if you start with mass in grams, you divide by the molar mass. If you start with, 20 liters, then divide by 22.4 to get moles. And then remember, this is always moles of what's given. And then this is always moles of what we want. Again, we get that middle step, we get those numbers from the balanced equation. And then if they want particles, multiply by 6.02 times 10 to the 23rd as an answer. If they want mass, multiply by molar mass. If they want volume, multiply by 22.4. Again, each one, we can use this to do any single problem. It'll be sitting in front of you when you're trying to work on them on a test. So anyways, that's it for doing stoichiometry. You'll have some problems to work on yourself. Good luck.